you very much for this opportunity to visit Kyoto University and also talk about some of the work I've been doing over the last too many years, 20, 30 years. So I'm going to be talking about my main interest, which is symmetries in Hamiltonian systems. It's 4 lectures, but there are 3 topics, and so roughly 1 per lecture. So I'm just showing this picture as an example of bifurcations that arise in a particular Hamiltonian system. But I'll explain when we get there what different things mean. So I want to put that away now. Can I take the screen up? Yes. So let me start very quickly at the beginning of what is a Hamiltonian system, Hamilton's equations. There are 2 ways to introduce them. One is more classical and the other more modern. So the classical So we have a function called the Hamiltonian. So the most usual example is where the Hamiltonian is kinetic energy and potential energy. So I hope you've all done some elementary mechanics courses to know what I'm talking about. Written in terms of position variables and momentum variables. And then the equations of motion are those. So this is two n variables. So the phase space is R2n. There are many examples where the phase space is not a vector space, but it's a manifold. And we'll see some examples later on. So so please interrupt, ask questions if I'm assuming you know something which you don't. Doesn't matter if you're a junior person or a senior person or something. We don't all know everything. So please just interrupt and ask questions. So does everybody know what a symplectic form is? Yeah? H, again, the Hamiltonian is a smooth function. Smooth could mean C2, C3. There's a famous paper of Moser where he assumes it's C333, I think, the KM theory. C infinity. So then I don't worry about how many times it's differentiable. Many theorems are proved for analytic Hamiltonians. So, well, the equations of motion, or Hamilton's equations, sometimes the vector field is put here, and sometimes the vector field is put here. It's just a formalism. It doesn't matter which convention. So once I went through, as an exercise, I went through all the different principal textbooks monographs and textbooks on classical mechanics, to see which was the right definition. So there was Arnold's book on mathematical methods of classical mechanics, Foundations of Mechanics by Abraham and Marsden, Lieberman and Marl, all these different books, and there was no agreement. So somewhere choices have to be made, and people make choices in different places. So or maybe dp wedge dq, depending which convention you use here. And yeah, so that's the setup. So omega, the important thing about the symplectic form, well, many important things, but in particular is it's non-degenerate. So this means that if we think of it as a linear map from vectors to covectors, perhaps, then it's invertible. So given dh, so let's say at the point M, so at each M, we have this equation. So given this, we can solve uniquely for the vector field. So this determines the vector field. So when you're studying a dynamical system, the first question is, a given dynamical system, the first question is, well, what we want to understand the dynamics. The most simple dynamics is equilibrium points. So let's start by talking about equilibrium points. Well, they're when the vector field is 0, or q dot and p dot are 0. And this is the same as the differential, or the gradient of the Hamiltonian is 0. So this is the condition for an equilibrium point. I expect everything I've said so far is very familiar to everybody. So then what happens near equilibrium? Or how do we discuss the dynamics? Well, the first step, well, first question is your equilibrium stable or unstable? And the second question is, well, we know that. Well, the two are not unrelated. What does the linear approximation look like? And third, if we understand the linear approximation, can we go from linear to nonlinear? Can we find out what the genuine nonlinear dynamics is? So these are all three things are related. So let's linearize first. So linear, if we look at so I should say in a neighborhood of a or locally, I should say, not locally. Is classical or has so we can always just locally study. I'm talking about the neighborhood of an equilibrium, not global dynamics at the moment. So we can always write it in this form. This is called Darboux Darboux's lemma. So that was known from late 1800s, 1890s. Forget. So let's suppose the origin P So this is like taking a Taylor expansion of the differential equation. D2H, this one is dq minus d2H d pi pj. So we're going to linearize, so we ignore the higher order terms. So I hope that's readable at the bottom. So let's write that matrix. So this is all second derivatives of H. So this is just a matrix of second derivatives, and J is so J is essentially the matrix for the symplectic structure. Actually, it's the inverse of the symplectic structure. But J has those two important properties. So this is the form of the linear approximation to this equation. So contrast, in general, non-Hamiltonian dynamics or differential equations, so if we have a differential equation like this, where L is not of this form, L is just the linear matrix for the differential equation, one asks about stability. So all the eigenvalues are in the left half plane. And if that's the case, you can say much more. There's a famous theorem the Hartmann-Grobman theorem implies the nonlinear dynamics is topologically, not smoothly, but topologically equivalent to the linear dynamics. So whenever, in fact, they don't have to be negative real part if they are not on the imaginary axis. If no eigenvalues are on the imaginary axis, then this is true. So this means that, so this is in a neighbourhood, this is a local result. In the neighbourhood of an equilibrium point. So we have an equilibrium point, and It doesn't require it to be not Hamiltonian. It just requires this condition. So that's a very strong information that you get for dynamical systems, for nonlinear dynamical systems. So, for example, if all the eigenvalues are on the negative side, then just by exponentiating the matrix L, you know that all the solutions in the linear system maybe spiral in towards the origin, but everything converges to the origin. So it's stable, and so this must be true for the nonlinear system as well. So, unfortunately, for most Hamiltonian systems, this is not very useful. So, in linear, so if we have an eigenvalue lambda, then so it's minus lambda. Of course, I'm assuming everything is real here, so this was complex plane, and you notice I drew them as complex conjugate pairs, which we all know. Any real matrix, the eigenvalues come in complex conjugate pairs. So here it's not only complex conjugate pairs, but also opposite lambda and minus lambda. So this isn't possible, because if the real part of one eigenvalue is negative, there's another eigenvalue whose real part is positive. So we can't. The proof, I won't go through the details, but you use this structure and shows that L transpose and minus L are conjugate matrices or similar matrices. With J, something. Maybe I have it here. So it's a little bit of linear algebra. So eigenvalues, the conclusion from this well, what are the possibilities? Well, of course, we can have 0. We can have a pair of real eigenvalues. A pair of imaginary eigenvalues. 0, I should say, is always double or even. That also follows from this general form. If S is degenerate, so 0 is an eigenvalue, then it turns out that it must have even multiplicity. And the final one is the sort of generic case called a quadruplet of eigenvalues. So because of this lemma, any Hamiltonian linear matrix, which is like this, has, maybe it's a large dimensional space with many, many eigenvalues, but it's a union of sets like these. So you can see at a glance this condition is not possible for all the eigenvalues. And this one, if we have real or we have quadruplets only, then we can apply the Hartmann-Grobman theorem to understand the dynamics. So it's hyperbolic and can apply the Hartmann-Grobman theorem. So that's the story for those. So with the real ones, we expect to see that's part of the system. And for quadruplets, it's not so easy to draw because we need 4 dimensions. So on one plane, it's attracting the spiral. That's the But the really interesting question is what happens when you have imaginary eigenvalues. Well, that's really what I want to talk about. And I'll come back to that. So I want to talk about bifurcations first. Well, no, I wanted to talk first. So the questions back here were stability, linear approximation, and then linear to nonlinear. So the main theorem about stability of equilibria is simple. And it was stated by Lagrange, essentially. Although Lagrange didn't write, of course, Hamilton was 100 years after Lagrange, but Lagrange was certainly talking about kinetic energy and potential energy. So at least he stated this for those systems, but it's more general. And it's usually called the Lagrange-Dirichlet criterion because Dirichlet proved it. Lagrange just stated it. It was evident to him, but Dirichlet gave a proof. Dirichlet was more than 100 years after Lagrange. So the Hessian matrix is a symmetric matrix, so all its eigenvalues are real. So there's a difference between the stability here, I haven't defined what stability means, and stability in this case. So this one is called asymptotic stability, and that can never happen for Hamiltonian systems. So the definition is there exists a neighbourhood U such that if x of 0, so x of t is a solution, x of 0 is in U, then x of t tends to the equilibrium point, the origin. So all nearby initial conditions converge to the origin. So here it was Lyapunov, who was after Dirichlet, who formalized what stability means in about 1900. So I'm going to come back to talking about this later. So I'm going to make a full statement now. For all neighborhoods U of, I'm calling the equilibrium point 0, so you need to play a game with two neighborhoods. You can't do it with one. So if we start we take a small neighborhood of the origin, then the dynamics might be quite irregular inside. But the point is, if you start with a V, necessarily from the statement of the theorem, V cannot be bigger than U. V is going to be smaller or equal. In many cases it's equal, but not always. So it might be some complicated motion. This is not a picture in the plane. This is in Rn. So if you start close, you can't go far away. That's the idea. Lyapunov wrote it in terms of epsilons and deltas. Nowadays we write it in terms of open sets, but it's the same. And essentially that is almost the only method to prove stability for a Hamiltonian equilibrium point. There are subtle arguments using KAM theory where you can, in low dimension only, that work in 2 degrees of freedom, but so n equals 2. But in generality, this is really the only method.
Excuse me, so your t can be negative?
Yes. Yes. So here, no. Here is what happens when t tends to plus infinity. So Hamiltonian systems, in fact, there are several theorems about Hamiltonian systems, which people then realize is really due to the fact that a Hamiltonian system behaves like a time-reversible system. So Hamiltonian systems are not always time-reversible, so the dynamics in the past is not necessarily the same as the dynamics in the future, but there's a lot of similarity, and certainly in all the cases of kinetic energy, potential energy type systems, mechanical systems, they are time-reversible. So there's everything, properties about t tending to plus infinity are also true when t tends to minus infinity. So that's essentially the only. I haven't said anything about symmetry yet, which is the topic. So let me come to that in a minute. So suppose we have a parameter, lambda. So lambda was eigenvalues there. Now it's a parameter. So as you vary a parameter, so this is where symmetry starts to be important. So the basic bifurcation is called saddle node. It has more than one name. So a schematic diagram depends which way lambda is increasing, or maybe lambda is increasing this way. It doesn't matter. I'll just draw a picture. So that curve. Let me draw it with a color. So bifurcation occurs at lambda 0. So if we take a value of lambda less than lambda 0, we have two equilibrium points. And as we move towards lambda 0, these two come together. They merge and they disappear like roots of a quadratic polynomial. Real roots of a quadratic polynomial, they become complex as you change the coefficients of the polynomial. So that's the basic picture of what's happening just for the family of equilibria. But then there are questions we can ask. So essentially this is a phenomenon that happens with 1 degree of freedom. I mean, it can happen in n, but the degeneracy, and I'll say why in a minute, is really about 1 degree of freedom. And the advantage of 1 degree of freedom, which means the dynamics is in two dimensions, we can draw pictures of the curves of the Hamiltonian, the level sets of the energy. So we might have so that would be the dynamics for lambda less than lambda 0. So there is one equilibrium point, yeah, but it's degenerate in a sense I'll make precise in a moment. And then there is no equilibrium point. So this is two equilibria. When lambda is less than lambda 0, they merge to give us one equilibrium, and then they vanish. So if we follow the curve, so we start up here and we come round and we follow the curve, which is not what's happening with the bifurcation parameter, but So we know at the bifurcation point we have a degenerate equilibrium. So the eigenvalues are going to be 0. On one side, we have an imaginary pair. And on the other side, we have a real pair. So we have two eigenvalues. So in an ordinary dynamical non-Hamiltonian system, you have two eigenvalues like this. Change the parameter, they would probably move off the axis because there's nothing to constrain it. Whereas this lemma I wrote before means that that's not possible because there's simple eigenvalues, and if we had one that moved off this way, we must also have one that way. And that's not possible because we don't have 4 eigenvalues, we only have 2. And then they move apart on the real axis. So this is called splitting. Because as I will see, it's not the only possible scenario, but it's the generic one if there's no symmetry. So let me sort of give a better feel for why this is happening, an actual calculation, and then I'll have a pause. So in some sense, you'll see what I mean. So L is J times a symmetric matrix. So right, JS. And J was the matrix I've written before. So that's going to be B C minus A minus B. Trace 0. And the determinant is AC minus B squared. Same as this determinant. But the important thing is it has trace 0. So what are the eigenvalues? T squared minus the trace of the matrix times T plus the determinant. So those are the eigenvalues. Now let's draw a picture. So ABC space. So that's 3 dimensions. And this AC minus, B squared minus AC, the bifurcation happens when the discriminant is 0. Let's see if I can draw this. B. So those are the three axes. This is a useful picture. So now we imagine we have ABC. The system depends on a parameter, lambda. So that means that this defines A, B, and C as a function of lambda is a curve in this space. So what does a curve do? Well, of course, a curve might be out here and have nothing to do with the cone, or it might be in here. But if there's going to be a bifurcation, then we need to have AC minus B squared equals 0 at some point. So where do you expect the curve to intersect? The cone? Maybe something like this. That's where it comes out of the cone. So it's inside. So this is my point ABC of lambda. And as it intersects the cone at some point, it could, of course, intersect at the origin, but that's unlikely. So much more likely is it's generically, it's going to intersect the cone outside the origin. So when AC equals B squared, the eigenvalues are both 0. But L is not 0. So it's nilpotent. So L squared is 0, but L is not 0. Okay, so that's the generic picture. And that picture, this is the generic bifurcation. And this picture sort of is supposed to convince you that this is what you expect. And the transition happens when L is not 0. But sometimes there might be some reason that L has to be actually the 0 matrix. So L is not nilpotent, L is semi-simple. Both the geometric multiplicity and algebraic multiplicity are both 2. So the curve is going through the origin. Perhaps inside the cone. Or outside the cone. And we're going to see this sort of thing is brought about by having symmetry in the system. Now, when you're inside the cone, which way is it? B squared is less than AC. And out here, B squared is greater than AC. So when B squared is less than AC, this is negative, so we get the eigenvalues are imaginary, both sides. Not, they don't split. This is called passing. So the eigenvalues go to 0 and they come out the other side. This is quite common in symmetric systems, we're going to see. And here's the real alternative. So if you look on books on bifurcation theory that discuss this, they will say this doesn't happen. It's unlikely to happen. And in order to have the curve pass through this point, you would need not just a one-parameter bifurcation, but a three-parameter bifurcation problem. Because if you've only got two parameters, then you would have a surface, and the surface is not likely to go through the origin. You'd need a three-parameter problem. So this occurs in three-parameter problems. So people say this has codimension 3. But we'll see in a minute or afterwards that in a symmetric problem, this happens a lot. So maybe I shall pause there for 15 minutes.